free!
That's what I'm talking about.
Wait!
Okay, now, from the beginning.
Welcome to day 3 of our PPI launching events, where we continue to explore the question, how do you turn adversity into opportunity? Normally, people come to Boulder for this. But instead, what you get today is this. But don't get disappointed. We have a special experience for you on Hopin today, and I'm so excited to introduce our co-host and the co-director of the Colorado side, Chang. Evan, take it from here.
Thank you, Danny. Hi, everyone. Welcome industry members, guests, or I should say future members, university colleagues, and students to day 3 of launching. With you, the Center on Pervasive Personalized Intelligence. We, and I personally, so appreciate you for joining us today and your infectious enthusiasm for this initiative. It has been a real privilege listening to your unique perspectives from industry and working with Danny, Shiv, Wenking, Eugene, and so many university faculty, staff, and administrators to get to this launch over the past 3+ years. But now, cool things truly begin. We have listened to and reflected on your feedback and made a number of improvements in the program to more effectively engage, connect, and ultimately advance the center together. We are learning together how to take the challenges thrown at us by the pandemic with this format on Hopin and turn them into strengths. Most importantly, we have made a number of changes that bring members closer in.
Or, as we say in the center, membership has its privileges.
Members have the opportunity to have both booths in the expo area to speak directly to the graduate students, as one of the key value propositions of being a member is access to industry-ready advanced graduate students for internships and employment.
Oh, you mean this is a sort of a speed dating?
Exactly, where students and employers get to connect and ultimately see if they're a match. Members will also be featured in the AMA Ask Me Anything panel, following the plenary project presentations. Members ultimately shape the direction of the center through serving on the IAB, the Industry Advisory Board, that influence funding decisions. The theme for today's session is edge computing, verification and programmability, and security and privacy. These topics complement the work proposed in the last meeting in realizing pervasive personalized intelligent applications. And it is this convergence of cross-cutting expertise that truly makes the PPI Center unique. We again begin with 6 executive summaries of proposed projects in rapid succession here on this stage. The speakers are available live, so please continue to make liberal use of the chat window to interact with them.
So how rapid is rapid?
Really rapid, 5 minutes. After the plenary talks conclude, we will immediately switch over to a plenary but interactive AMA session with a panel of today's speakers and representatives from member companies in the sessions area. To join the conversation live, click the blue button to share your audio and video. You may not show up immediately and instead be held in a waiting area, but please do not drop off. Today's AMA session moderator, Wenking Wang, will bring you in right away. Based on your feedback, we have extended the AMA time and moved to a single small group meeting session. After the AMA session closes, there are 5 minutes for us to take a quick screen break or to hop into speed networking.
Oh, this might also be a good time for a bio break, but please make sure to turn off your camera and your microphone.
Now, in speed networking, if you choose to do that, remember to hit the blue connect button to exchange a virtual business card before the 2 minutes are up.
It's as if we were exchanging a business card at an in-person event.
That's right. Then, at 5:05 Mountain Time, head over to the sessions area to join one of 3 small groups meeting on edge computing, programmability, or verification, security, and privacy. These are intended to be meetings at a virtual roundtable.
You mean like in a Zoom?
Well, not exactly. On the Hopin platform, you do need to click the blue button to share your audio and video when you arrive. You can, of course, freely move between the 3 parallel breakout rooms.
You mean I can hop in and go between 3 rooms at the same time?
That is one advantage here that we have today that we wouldn't have in a live event. After the small group meetings, head to the expo to talk with Danny at the Yes desk, or with our extremely kind, friendly, and helpful NSF representative, Dee Hoffman, or of course, meet someone new in speed networking. And students, Make sure to go meet your potential future employers at member booths also in the expo area. Finally, let me conclude this welcome by asking for your help to help you advocate with your organization. Think about colleagues and thought leaders at your organization you want here. There are still 3 more events to come in this launch. Start with ppicenter.org, where you can find and share a one-page flyer or the overall agenda for this series. Help them catch up with the pre-recorded content, but also convey how much they're missing by missing out on the unrecorded live sessions. With that, together we go farther.
Hello everyone, the title of my project is System Support to Enable AI at the Edge. Let me motivate this project through 3 IoT applications. First, consider a public space with large moving crowd, such as an airport or a shopping mall with cameras at various locations, and our task is to identify people and track their movement. Next, consider a precision agriculture application, where various agriculture sensors are embedded in the field, and a drone flies over, streaming images of the field. Our task is to perform smart irrigation, appropriate fertilizer application, and weed control. Finally, consider a smart city that has various kinds of sensors embedded, and our task is to manage various city operations such as water and energy distribution, traffic management, public safety, and so on. So in all these applications, we need to perform compute-intensive tasks that are context-aware, privacy-preserving, and provide results in real or near real time. In order to address these requirements, the smart city environment is augmented with 1 or more edge servers, essentially a mini data center that is close to the data sources. The edge server includes storage and CPUs, and more importantly, various kinds of specialized accelerators, such as GPUs, FPGAs, and other ASICs. However, there are several challenges in edge computing at present. There is a lack of system support, and the application developers have to deal with complex issues of device processing and network heterogeneity with minimal support for resource sharing. This brings us to the long-term goal of our project, which is to develop system-level support to facilitate compute-intensive AI applications at the edge. There are 3 important characteristics here. First, we'll develop a flexible microservice-based architecture comprised of different OS abstractions such as containers, VMs, serverless concepts, runtime environments, as well as traditional process and thread abstractions. Second, we will utilize diverse computing resources, including sensors, smartphones, drones, as well as servers comprised of CPUs, GPUs, FPGAs, and other ASICs. Finally, we'll tightly integrate humans in the loop, both as data generators and data consumers. Our short-term goals in year 1 include investigating distributed execution of AI algorithms over CPUs, GPUs, and FPGAs, and developing individual components of the microservice architecture. And in year 2, extending our AI algorithm implementation to distribute fluidly, meaning determining the distribution parameters at runtime based on current context to satisfy latency, cost, and privacy requirements. We'll first integrate 2 tools that we have developed with Kubernetes. The first one is Shimmy, which provides an efficient inter-container communication mechanism, and the second is Dynamic Graphs, which provides dynamic orchestration of containers on demand. We'll also investigate integrating serverless solutions for the edge. We'll also experiment with several popular AI algorithms such as face recognition, gesture recognition, and anomaly detection by distributing the computation fluidly using current state-of-the-art programming models such as OneAPI. This research project is leveraged by more than $3 million of funding from NSF that we have at present, and a very active collaboration with the city of Denver, several nonprofits, and several low socioeconomic communities in Denver. Further, our research is interdisciplinary in nature, with active collaborations with researchers from environmental engineering, social science, and education departments. In terms of deliverables, in year 1, we will release a Kubernetes-compatible dynamic container orchestration tool, prototype implementations of popular AI algorithms over CPUs, GPUs, and FPGAs, and an edge serverless solution by integrating Firecracker into OpenWhisk. In year 2, we'll release an extended version of AI algorithm implementations by incorporating fluidity, and finally release our microservice-based architecture for edge computing. So in summary, edge computing is the key driving technology for IoT systems and a smart city. The key problem is that building AI applications at the edge is a complex task at present. Our proposed solution is to build a microservice-based architecture, and there will be several deliverables throughout the course of this project. Thank you for listening to my presentation. I'm really excited and looking forward to interacting with our industry partners. Please ask any questions during the upcoming Ask Me Anything session and join me in my small group discussion breakout session to discuss project details, provide suggestions, and essentially help me take this project forward with your collaborations.
This project is about using the network as a reusable programming platform. This is a joint work with my colleague, Dirk Grunwald. The network has become more intelligent and softwareized. The trend toward more programmability and flexibility in the networks make it possible to program everything, including network interface card at end host, where the packets are sent and received, and the intermediate network devices such as switches and routers. Software-defined radio platforms have also enabled programming wireless physical layers. This new trend of using the network as a programmable platform enables unprecedented research opportunities for emerging edge and IoT applications. Imagine that heavy machine learning computation of IoT applications is transparently uploaded into the network hardware, or the network efficiently handles the complex consensus procedures of multiple edge applications. In practice, however, an individual application might implement non-reusable proprietary code to upload part of each application into the network, resulting in time-consuming duplicate effort. Given that network applications have many common functions or primitives that could be uploaded into the programmable hardware, why not develop such standard primitives to facilitate a variety of IoT and edge applications? Our research object is, instead of uploading individual applications into the network, we develop reusable primitives that can take advantage of modern network hardware to help upload common system components of a broad range of edge and IoT applications. This project will be conducted for 2 years. We will identify the list of reusable network primitives commonly used for various network applications in year 1. In year 2, we develop those primitives using P4, a data plane programming language, and evaluate them with real applications. So as you can see from the figure of the programmable network card, modern network systems operations generally separate their execution into 2 phases. The fast pass is a typical case of failure-free operations, and so usually improving the fast pass is the most efficient way to enhance access latency, throughput, and scalability. On the other hand, the slow pass is used to recover from errors, and so its processing is relatively slow compared to the fast pass operations. In our project, we design, implement, and evaluate reusable network primitives that can execute in the fast pass, which can significantly improve latency, performance, and scalability of the network applications. This project also leveraged the past and current award from NSF and NIST, which has a total of $2.1 million. Deliverables and outcomes. In year 1, we will release a survey paper that describes the list of reusable network primitives for various network applications. We also provide sample code of those primitives for network reliability and also tutorials for industry members. In year 2, we will publish a research paper that describes the design and implementation of a practical network application built on top of these primitives. We then provide software code for representative application along with reusable network primitives we have developed. We will also offer tutorials for our industry members. In summary, we will develop reusable network primitives that can be uploaded into the programmable hardware to enhance edge and IoT applications performance. For that, we divide the process execution of the network application into 2 phases, fast pass and slow pass, and identify the list of reusable network primitives that can benefit from running on the programmable hardware and implement them. We expect that emerging edge and IoT application can leverage network hardware to enhance their latency, throughput, and scalability. Our deliverables include research papers, source code, and tutorials for industry members. We are committed to working with the industry partners to shape our research directions. Thank you.
Hi, I'm excited to share my proposal on privacy-preserving data reconciliation. So this proposal concerns problems related to data processing, which would be quite straightforward if all of the data was centralized in one place. But in reality, the data simply can't be centralized. So I can illustrate with a simple example. So imagine a database with a table of advertisement impressions and another table with a list of purchases. And suppose we wanted to know how much was spent by people who saw a particular ad. We can answer this question easily with a simple SQL query on these tables. But what if these tables weren't sitting together in the same database? What if one table was held by an advertising company and the other table was held by a brick and mortar store? So in this scenario, neither company wants to grant access to their customer data in a way that would allow us to answer this SQL query. So I propose a way to perform queries on private data that's distributed. So instead of centralizing all the data for processing, we can rely on cryptographic techniques to process that data without anyone being able to see all of the data in the clear. So the long-term vision is enabling a non-trivial subset of SQL on data that's distributed in this way. But within the time frame of the project, I think we'll be able to support a small but still useful subset of SQL involving joins and aggregations on the data. So for example, if the participants agree to do a simple join over their tables, they'll learn exactly which items they have in common, but they won't learn anything about any other items. Or the participants could agree to learn only how many items they have in common, or maybe some simple aggregate information over those items. And in those cases, they wouldn't even learn which specific items they had in common, only the result of the aggregation. I also want to highlight two other building blocks that will be useful in eventually unlocking more sophisticated subsets of SQL. The first is to allow the participants to learn encrypted representations of their common items. I think this will be useful in composing different SQL operations together without leaking information about the intermediate results. And another one is to assign random identifiers to all the items so that common items get common identifiers. And this can be done without revealing which items are common. But now having a common set of identifiers should help with further processing. And I just want to emphasize that the novelty here is not that we're doing any sophisticated data processing. You see that all these SQL statements that I have as examples, they're pretty simple. The novelty is that we're doing any data processing at all without being able to really see the data. Of course, if you have a really complicated or expensive data processing in mind, it would be even more expensive if you did it inside a layer of cryptography. So that's not exactly what we're going for here. So we can do this kind of processing on distributed data with state-of-the-art cryptographic protocols. And the cryptography research group here at Oregon State happens to be one of the world leaders in protocols for something called private set intersection. That's the simplest of the examples that I mentioned on the previous slide. And we've implemented and developed the best and the fastest protocols for this intersection problem. And in this project, we'll adapt those techniques to the related problems that I mentioned where more partial information needs to be hidden. These kinds of cryptographic problems are the bread and butter of what we do here at OSU. And we've been supported by funding from Google, Facebook, et cetera. You can see that on the slide here. So as part of the project, we'll develop new cryptographic designs that go beyond the simplest cases that I mentioned. All of the work that we do in cryptography here comes with formal proofs of security. So we're not giving you heuristic security, we're giving you the strongest foundation of security that's possible within the cryptographic research community. We'll provide usable open source library implementations of our protocols, not just research prototypes. And over the course of 2 years, we'll enable larger and larger subset of SQL features following the roadmap that I mentioned earlier. We'll deliver white papers that communicate the security and performance properties in a way that will let you make informed decisions, even without deep cryptographic expertise. And finally, in year 2, we'll work with you on integrating these crypto libraries into your data sources. So in summary, I propose tools that will help you do processing on distributed and private data. So you'll be able to use state-of-the-art cryptographic protocols to make specific controlled queries to distributed data that release nothing else about that data. And this will allow you to get insights on data even when you can't collect all of it centrally. So we'll empower you to use these fancy cryptographic technologies even if you don't have a crypto R&D department. So we can be your crypto R&D department, basically. So thanks for your time. Remember, we're eager to get your verbal feedback and your written feedback about these proposals. Thanks.
All right, so I'm excited to talk to you about conformance verification for machine learning models. Machine learning frameworks such as TensorFlow are wonderful things. You start with data and a model structure, and you build a prediction model that minimizes the error between what the model says the output should be and what the data says it should be. And accuracy here is the most important thing that these frameworks try to minimize. And this has found a lot of applications in business decision support, or in real-time control in medical devices or self-driving car, or warnings and advisories in medicine and business and in a lot of domains. We have worked with this framework in 2 different domains. One for regulating insulin delivery in people with type 1 diabetes, where we use machine learning to tell us if you give a certain amount of insulin to a patient at this time, what's going to be the future blood glucose level of this patient? And we can use that to base treatment decisions. Likewise, in self-driving cars, you can have models that take the current state of the vehicle, the throttle or the brakes that you apply, the steering that you apply, and tells you where the vehicle is going to be in the future. But what we have found is that accurate models in these domains are not safe to use models. A model can be perfectly accurate and still have something wrong in it. In type 1 diabetes, we find a conformance property. That is, we want the model given more insulin to predict a lower blood glucose level. Unfortunately, we found that it doesn't happen even for highly accurate models. In self-driving cars, we want more brakes to mean that the car goes slower in the future. Unfortunately, again, we have found that it doesn't happen even for widely used and accurate models, and you can see the details in some of our papers. So in this project, we would like to talk about specification. How do you talk about conformance? How do you specify the conformance property that you are interested in your application domain? And how do we express them in a formal way so that we can do verification and falsification? We can prove conformance. We can prove that your model is not just accurate, but hey, it's also conformant. Or we can find counterexamples where it's realistic and you would say, look at it and say, hey, my model is really wrong here. How do I go fix it? And these are the shorter term goals. In the longer term, I would like to talk about data debugging. I would like to consider the entire pipeline from the data to the training and figure out where do these conformance violations come in. How can we do things differently, collect the data differently, train the model differently, structure the model differently, so that these violations are gone even before a model is trained. And that's a long-term ambition that I would like to work on with you in this project. So in terms of our approach, we have 2 years, and we are going to spend year 1 working with you, our industry partners and our industry members, to find application domains that are of interest to you, where we would like to try our existing solutions out. We have a tool called Sherlock that we have built, and we would like to see how do these tools do on applications for conformance properties that you are interested in. In the second year, I would like to work with you, our industry members, on solving something with integrated specification and verification mechanisms. Try to integrate them into TensorFlow or whatever framework you try to use internally and see where we go from there, and work with you on these longer term problems like data debugging. A lot of this is supported by existing funding we have gotten from NSF and the Juvenile Diabetes Research Foundation. NSF is funding us for the basic research, and Juvenile Diabetes Research Foundation is funding us to look at how do you do type 1 diabetes treatment based on data. And we have tools, like I mentioned, Sherlock, that are already available that can be a good start for our partnership. So in terms of deliverables and outcomes, in year one, we would like to deliver some case study reports working with you and finding out the conformance properties that matter to you. We would like to talk about specification formalisms and prototype and integrated analysis tool. In year two, we would like to work on richer specification languages with better integrations inside the machine learning frameworks that you use inside your groups for machine learning and see how we can do conformance verification there. And like I mentioned, work towards the longer term goals, the harder goals of understanding the root causes and fixing these issues. So to summarize my talk, we would like to talk about machine learning, not just in terms of getting accurate classifiers with low errors, but also try and get models that must satisfy important properties. We have ongoing basic research that has already been supported by existing grants, ongoing tools, and some papers. But we would like to work with you and take this research to the next level and make it relevant to real industry applications that come from your industry. Thank you, and we look forward to the small group discussions. See you there.
When we think about the tools of the trade for software engineers today, they're pretty basic. Text editors or integrated development environments, version control repositories, emulators, and perhaps continuous integration and deployment pipelines, where quality is achieved through expensive manual processes like code review and manual QA testing. I work in the area of automated program analysis, where I develop algorithmic techniques that assist your software engineers in reasoning about code they're writing. Today, I want to present a vision of giving your engineers the intelligent tools they need to create reliable, safe, and secure, pervasive, personalized, intelligent products that your customers love. When we think about the future of IoT and pervasive, personalized, intelligent applications, we think about the end products, like driverless tractors or autonomous trucks that realize smart agriculture or smart logistics. But not so much about the complex and fragmented software stack needed to realize smart products. That is, of course, until they crash. Ooh. At which point, your engineers are under incredible pressure to quickly diagnose and fix the issue, and could use all the help they can get. Of course, there are a huge number of technologies and frameworks that abstract different parts of this stack. And a key reason I'm speaking to you today is to learn about your stack and better understand the software quality pain points that keep you up at night, or that repeatedly page your engineers at all hours. In the meantime, let me use Android as a common example of a large and complex software framework that is pervasive in this space, and where you have some prior work in imagining such intelligent software development assistance. Back to your engineers' cry for help. Fortunately, for any important enough framework like Android, there's a community of developers using that framework. Your engineer is not alone, and faced with desperately trying to fix the issue quickly, perhaps in the middle of the night, he is hoping that someone else, maybe at your company or not, has sweated through finding the same issue, figured out the fix, and committed the fix into a code repository where he can then use the fix in his context. Thus, the vision is to develop the fundamental program analysis and synthesis techniques to assist your engineer in transferring bug fixes confidently and reliably, and thereby also amplifying any effort spent in finding and fixing issues through sweat and tears. Ultimately, the long-term objective is to create intelligent, data-driven tools that leverage communities of developers to help your engineer diagnose, repair, and verify PPI apps. Short-term, we will study, design, and apply. Study how you develop or might develop pervasive, personalized, intelligent applications today. Learn about the shortcomings of such software frameworks that enable designing tools that leverage state-of-the-art, data-driven, and algorithmic program analysis engines. Work with you to make these techniques effective for your engineers. We will advance in the state-of-the-art in development tools for quality and security, addressing the unique challenges of intelligent IoT software. The essence of our approach is that while it is clearly infeasible to test or simulate, for example, all possible event interleavings for your system, we have developed a number of techniques that make such reasoning goal-directed to cut through the exponential reasoning space, paired with techniques that extract patterns from code repositories. This work leverages a recently completed $1.9 million DARPA-funded project on mining and understanding bug fixes, as well as an additional $7.2 million of DARPA and NSF investments in fundamental research projects. This is a 2-year project that will deliver the following results. In year 1, we will identify and curate a repository of common defects, important assertions, and reasoning challenges in the most relevant software frameworks for creating PPI apps. In year 2, we will develop automated reasoning techniques and release tools that address the most pressing issues for your engineers. To summarize, our ultimate goal is to create intelligent, data-driven tools that leverage communities of developers to help your engineer diagnose, repair, and verify PPI apps. Through a combination of mining code repositories and automated reasoning techniques, addressing unique challenges of pervasive personalized intelligent applications, you get additional confidence in your product's quality and potentially QA savings, earning trust in products that your customers love. By giving your engineers access to state-of-the-art tools, even without an automated reasoning R&D department. I truly appreciate your questions and look forward to hearing what keeps you or your engineers up at night in the small group discussion. Thank you.
I'm so excited to talk about a software engineering problem. Code bases need to continuously evolve in order to remain useful. This was already a hard problem even for traditional software systems, but it's even harder now for machine learning code bases. How do we maintain and how do we evolve software that contains machine learning components? It is widely known that at least 2/3 of software costs are due to evolution, and some industrial surveys claim even 90%. Let's meet Jimmy, a software and data engineer at your IoT company, who decides to use TensorFlow. Let's look at some unique challenges that Jimmy faces every day when evolving his code. You see, Jimmy needs to constantly change his code to use newer APIs for TensorFlow, but he accepts this is normal. This is just part of traditional software development. What's different now is that Jimmy has pressure to evolve his code from 2 new directions, when the data changes and when the machine learning models change. It's no wonder that Jimmy feels like prey being torn in opposite directions by 3 crocodiles. For example, Jimmy will need to migrate his code from the eager mode in TensorFlow, which is great for fast prototyping, to the static mode, which is significantly more efficient. Furthermore, to optimize performance, Jimmy also has to replace loops with highly efficient NumPy algorithms and has to do many, many more other changes. See, unlike in traditional software development where Jimmy has IDEs and tools to help him change the code, when it comes to performing these machine learning related code changes, there is no tool support. So poor Jimmy makes all these changes by hand. These changes are too many, they are error prone and time consuming. This is what makes machine learning code development expensive and prevents his company from innovating in the marketplace. Our novel idea is to come alongside Jimmy and to bring his toolset into the 21st century. We will semi-automate some machine learning related code changes with some software tools and make Jimmy productive and happy again. Our approach is to offer interactive automated program transformations that put Jimmy in control. He has the intuition, he's the data expert, and he has the domain knowledge, and we let the software tools do the heavy lifting to search and to remember and to compute. In the long term, we want to mechanize many kinds of software changes that are required when using machine learning components. But in the short term, in year 1, we will first need to understand what are some common software changes for machine learning components. So we will focus on transformations to optimize performance. My group has a track record of starting a new research direction with formative studies. This helps us understand what's the pain point that developers have, and this also ensures that we are solving the right problem. In year 2, grounded on such formative findings, we will design, will implement, evaluate, deploy these tools as interactive programming refactoring tools. You see, to learn these common changes, we will first develop a pattern mining tool. We will rely on our previous fine-grained representation of code changes that uses very precise information such as program dependence graphs. Next, we will deploy these pattern mining tools on a repository of top 3,000 open source Python machine learning code bases. And we are also committed to work with you in industry to also deploy our tools and to learn common changes from your proprietary code bases. Now, based on these formative studies, we will deliver refactoring tools. We will integrate with IDEs that are used by you, our industry members, and we will work with you to deploy in your production environment. This project leverages more than $3 million of past and current awards from the National Science Foundation and multiple awards from industry. And my research group has a track record of contributing our previous refactoring tools, and they ship with official list of development environments which are used daily by millions of Java and C# programmers. And we will, of course, leverage such key relationships. In year one, we will curate a repository of best practices, and this will be a tremendous educational resource for your engineers. Second, we will catalog these best practices into design patterns and tutorials, and we already have experience with conducting this kind of work. Our industry tutorials for async programming were used by more than 150,000 engineers. Second, we are also going to deliver tools to automate changes for these machine learning components. First year, we will release a reusable framework for mining frequent code changes in Python machine learning code bases, and we will train your engineers so that they can deploy in their own proprietary code. And in the second year, we will release refactoring tools as plugins for the IDEs that are used by you in industry. It's been said that change is the only guaranteed constant. Machine learning code bases need also to evolve in order to remain useful. But this is currently done manually. Our solution is to build interactive program analysis and transformations for changing machine learning code bases. We will develop such tools grounded in the formative studies of both real-world changes in open source and also code bases used at you in industry. We will deliver a curated repository of best practices, industry tutorials, usable software tools, and we are committed to work with you in industry to steer our direction using an iterative process. Every 6 months, we'll present progress, we will collect your feedback, this will help us improve and re-enter, and that's how we are going to better serve you in industry. I'm looking forward to the discussion in the small groups. Together, we go farther.